Right, good afternoon, everyone. Get started because we only have 25 minutes, and I'm notorious for using all 25 minutes. So we can talk a little bit about building and operating an open compute style data center at small scale. This is up in the north of Sweden. So my name's Dr. Jon Summers. I'm working as a research leader at Research Institutes of Sweden, which is kind of like a research institute that's around Sweden. We are at the most northern part, right on the edge of the Arctic Circle, and there's lots of reasons why data centers should be up there. We have a lot of friendly neighbors as well. So the agenda here is really just to tell you what is this Boden-type data center, Boden-type degC project. I'll talk a little bit about the design of this OCP-style data center at small scale. Talk about the way that, because this is a EU-funded project, so it's not a business data center, it's a test data center, if you like, a pilot data center. We are collecting lots of data around the energy efficiency of the data center. So we have created an open source monitoring tool, which is a chain of open source software, which we're using to collect data. I will show you some operational results, and depending on the internet connection here, I will try and connect all the way up to the 66th parallel on the Arctic Circle and show you some live results from the data center operating now. So there's some pictures there of the actual data center. It's in a traditional red style color for the region of northern Sweden. And you can see inside there some of the cooling units and OCP servers, repurposed OCP servers, recycled. So we are reusing some OCP servers that were donated to us. So just in case you haven't got your geography sorted out, the red dot there is where Boden is, which is about 30 kilometers up the river Luleå from Luleå. And I took this from Google Maps so you can see where I actually live, the blue dot. So I do a lot of shameful miles by air. But this project is really to build a pilot of a data center which is cost and energy efficient at sub 1 megawatt, and to prototype that. So the data center is located in Boden, as I say, and you can see this nice black and white picture here, snowy picture of Boden taken in the winter months. There is the Luleå River, which is not too far away there. The most important thing for the data center is the hydroelectric plant over here. So this is renewable energy, and we're not using this, but we've pointed out the biogas plant for possible future use. Our friendly neighbors here, Hydro 66, who are here as well, and the project site location is here. Okay? So why did the EU want to fund such a project? Well, I mean, everybody knows, you've seen some talks this morning, that the energy growth or the carbon emissions from this industry is going up, and we all like to talk about efficiency, and regrettably, I will make reference to the PUE, which isn't an energy efficiency metric, but it's something that the call was focusing on. So they wanted something that was a low PUE, whatever a low PUE means. Some reference there for EU data centers. So we're talking about Europe here. Bertoldi is part of the JRC, the Joint Research Council. He collects information on the EU Code of Conduct of information about data centers. Not all of them are in Europe, but a lot of them are in Europe, and he was referring to the projected 104 terawatts hours of energy consumption by 2020. So if we are to prove that this data center is energy efficient in some way, and then we need to have some kind of comprehensive monitoring and measurement of it. Now, the reason why I said it's kind of an OCP style is that we don't have a centralized UPS. We use direct fresh air with filters, and we use water to humidify or to use it for evaporative cooling. And we're obviously one of the pods, there are 3 pods in the data center. One of the pods is based on legacy OCP equipment. And I must say that, so the actual call was bringing to market more energy efficient and integrated data centers. So being an EU-funded project, it's not just us at RISE. We have partners, H1 Systems from Hungary, EcoCooling from the UK, Boden Business Agency from Sweden, and Fraunhofer from Germany involved in this project. So this is what it looks like in the snowy conditions. It went live in January this year, 2019. And the pod 1, which is the OCP hall, has 4 cooling units, and we have 4 triplets here, which is nominal, max peak performance of around about 140 kilowatts of legacy OCP. And it's designed in, as you know, the OCP design when you use fresh air, particularly in these climates, is that you have to recirculate the air inside. So this air coming outside can be as low as minus 30 degrees centigrade. So what you want to do is recirculate some of the heat from the IT equipment, and mix it with the incoming air to get your desired temperature. And that's exactly how the original OCP data center was designed as well. And of course, we waste the excess wasted heat from the roof there. That's why the design is as such. So, this issue of free cooling using fresh air, this is a cumulative plot for Boden of the number of hours in the year, being 8,600 and something hours, that is, say, below zero. And it says here, this is about 3,000 hours per year are below 0 degrees centigrade. And if you like, the IT equipment is very comfortable at 20 degrees centigrade, and even there, it's more than 8,000 hours per year that are less than 20 degrees centigrade outside. So very, very efficient way, if you like, of using the local climate to cool the IT. So we talked about this chain of monitoring. This is a very complex diagram, so I apologize. But this has grown out of the Research Institute RISE over a couple of years. It's basically what we need to do is we're using a number of different protocols to connect to the various components that are monitoring aspects of the data center. So the environment, for example, we have a weather station, the energy meters, all the power that's coming into the data center and is distributed to the racks, etc. We're also looking at what's happening on the cooling side. So the fans, there are 8 fans in this pod 1, 4 for supply, 4 for exhaust. And also we're monitoring water consumption as well, because we will use water to humidify. The interesting thing is the IT, and I want to talk a little bit more about this in a minute, because we have built a little bit of hardware which sits in between the motherboard and the fans in the IT. Basically, we've got 1,000 server fans in this data center that we have taken control of. And that's what I wanted to sort of focus on today, to look at this kind of holistic cooling approach, or integrated cooling approach. And that the monitoring system, this all goes into Zabbix here, and Zabbix gets very upset by the amount of data it gets, so we have to offload it through streaming protocol based on Kafka into a long-term storage database, Kairos DB, all open source software. In order to actually understand how the IT behaves, we built, with the help of our partners here at Jetic, we built this wind tunnel, which is basically a recirculation of air, so you can supply the air at a certain speed. You have a heat exchanger here, so you can change the temperature. And the idea is to create a pressure drop across your server at a particular temperature, and then monitor the delta T across the server, because that's very important for running these IT systems. What is the temperature drop? And that enabled us to do some standard estimates of when 480 of these are in the actual pod, what the delta T is expected across the total server, the total equipment. This is some pictures of the actual wind tunnel that was designed and built here at RISE. So we have the ability, also the monitoring and the monitoring of the IT is all connected to this open source monitoring system as well. And we can control the fans and the fan and the temperature of supply to the IT at the upstream. So interestingly, these are windmill servers, so you will say, gosh, that's really old. And we have a few things to say about the windmill servers, but obviously we'll not talk about that today. But interestingly, as you increase the load on the CPU, so this is a percentage of CPU utilization for one of the servers, you can see that depending on the input temperature, here there's different input temperatures, up to 30 degrees we went. You can see there's a difference in power draw. Now you could say, that's the fans. It is mostly the fans, but some of it is obviously the current leakage as well, as you increase the temperatures of the CPU. So the fans do actually consume quite a bit of energy, and when I come to this holistic cooling control in a minute, you'll see how much energy that actually is. So what we were able to do for one server, we were able to assess its normal operation, default operation if you like, where we don't have control of the server fan. We were able to assess what the delta T was across it. So, you know, from idle, it was at 7 degrees to a peak of around about 13 degrees at full load. So what we wanted to do, and putting all this together in the data center with 480 of these servers, we wanted to first create an arrangement where the cooling units could actually pick up some aggregate data from the IT equipment. So what the cooling units are doing is they're supplying air into this cold aisle. Now if they supply too much air, obviously the pressure goes up. And if you're pressurizing the cold aisle, then you are wasting a bit of energy in a sense. What you want to do is try and match the supply flow rate to the flow rate through the IT equipment. So our first phase that we've actually achieved here in holistic control is actually linking together the aggregate information from the IT equipment to the cooling units. And that enabled us to trim back the fans on the cooling fans, which are contributing to the other side of the one on the PUE, and reduce that and allow us to run with a better PUE. But really what I'm going to focus on today is this phase 2, where what we've done is we've taken control of the CPU fans. Now again, we've gone back to our wind tunnel and we said we want the CPU to run at 75 centigrade all the time, irrespective of the workload. And that then will give us a constant delta T, which the cooling units can synchronize to. Now to do that, obviously you need to understand, we need to take control of the fans, we need to change the fan speed so that the CPU temperature is maintained, or the maximum CPU temperatures. These windmill servers have 2 CPUs. It depends which one is doing the workload, but one of them is always hotter than the other, and it's the maximum CPU temperature that we're holding at 75 degrees centigrade in this second phase. These are the cooling units from EcoCooling. Basically, they're just ventilation systems. They ventilate air from outside, and they have dampers which allow us to recirculate air. But they also have wetted pads, which means we can wet the pad and then humidify the air. Now, the challenge is in this climate is if you wet the pad and then allow the minus 30 degrees centigrade temperature to come in over the wetted pads, you freeze them. So what we do is, because we've got 4 of them, you run 2 of them in recirculation mode. So no outside air comes in, and the other 2 run, and this actually works really well. So we were seeing, in the winter months, we were seeing humidities in the cold aisle of as low as 2 or 3%, which is not ideal at all. And with this approach, we were able to raise this to 30%, 35% humidity. That's the IT equipment. So in the first phase, what we did is, you can see here that this is the controller, this is the master controller for the coolers. We dialed in a percentage speed for the fans with the expected delta T that we got from the wind tunnel, so that the fans in the coolers would synchronize to that. That was the first stage. What I wanted to show you here is that also we're monitoring the cooling power here, 1200 watts, for idle power here, 43.1 kilowatts. So this was our PUE very early on of 1.03. The average fan speed was 2,540 RPM, and you can see here at idle the delta T is 7.5 degrees. So the delta T is too low, the fans are running too fast, the cooling fans are running too fast, and the server fans are running too fast. So that's what we wanted to concentrate on to try and make this a bit more energy efficient. Before I go into those results, I just wanted to say briefly how we if you're running a test data center, you don't have any customers, there's a challenge. Challenge is what kind of workload do you give it? So we have developed, with the help of my colleagues here, Daniel here sitting at the front here has developed this workload scheduler, which allows us to deploy workloads on the data center in a very, very neat way. And it's based on containerized workloads, so the workloads are already in containers, Docker containers, and then we use Kubernetes as a way of deploying it onto the data center. So we can choose, we can dial in a percentage CPU utilization for the whole of the data center, for one of the racks, for half of one side of the data center, the other side, so it gives us a lot of control. Fraunhofer are our partners who are very interested in IoT workloads, Internet of Things workloads. So they have created application-orientated workloads which are based on predictive maintenance and smart cities. So they have taken data from existing setups and replayed that using a very clever way of building up the application workload. And that runs, it's a very noisy workload, much more noisy than our synthetic workloads, but we also have that kind of workload on the data center as well. So this allows us to set up jobs and we can see what has been run and monitor the cluster through this tool as well. So, I'm getting close to running out of time, aren't I? It always happens, this. There's always too much to tell. So this is actually a profile of utilization, CPU utilization, and the different colors are the different racks. So it demonstrates how we will see our workloads through Grafana, okay? And the corresponding power that's consumed by the data center is on this slide here. At the same time, you can see the idle power here going up to a 80 kilowatt load here and then up to 100 kilowatt load here. And this is the facility power, or the remainder of the power that's consumed by the lights, the cooling equipment, etc., which allows us to calculate the PUE. So we got a 30-day PUE, average PUE here of 1.037. Remember, PUE should be is averaged over a time period, and if you go with the ISO standard, it should be averaged over a year. It's annualized usually. We don't have a year's worth of data yet, so we can't give you the annual PUE yet. But the important thing here is to note, going back to this graph, 7 degrees on one server at delta T at idle and 13. You can see here this purple curve here is the delta T. The delta T is measured on this axis here. So you can see at idle here it's about 7 degrees here. And at peak, it's around about 13 degrees. So this scales up from one server to 480 servers, it scales up. So the analysis we did in the wind tunnel scales up nicely. But now this is what you see in terms of the pressure. So as I said, you know, if we overpressurize by 1 Pascal here, so this is the cooling fans providing too much air here. So when the workloads increases, the cooling fans are saying, oh, I need to bring more air in because the server fans have increased, so they're taking more air away, so I need to respond to that, and this is not a very well synchronized setup. But what really happens when we do put these fan controllers in, and that's hopefully here the pièce de résistance in this. So these are some pictures of the windmill servers inside. We have actually done some tests of copper heat sinks versus the cheap aluminium, brazed aluminium with heat pipe heat sinks which are in the servers. But here you can see where the fan controller has been, so it's a little bit of, it's on a little IC which has been plugged into the main board, and it interrupts the signal between the motherboard and the fans. Now it runs in a way that if things go wrong, it gives back control to the motherboard, because obviously we don't want to set fire to anything. But most of the time we can take control. And these are some of the results that we've managed to gain. So first of all, remember, this is, let me get this right now. This is the power, this is the aggregated power consumed by all the fans at idle. Okay? Over 600 watts, 1,000 fans, right? Then we said let rack 5, we got 4 triplets. Let rack 5, let's take control and say keep the CPU at 75 degrees centigrade. It's idle. Its CPU temperature is much lower than that at idle. Okay, then obviously the fans drop back, so we save some fan energy. Then we asked the whole data center to do it, and we almost got down to 0 watts on the fans. It's idle. So the cooling fans are providing enough air, because these are 2 open U servers, for the air to travel through the servers, and you don't need the server fans at idle, almost. And you can see here that the delta T here has risen up here from nearly, I think this is in, I can't quite see it there, let me see it on the screen here. It's challengingly small, isn't it? 14 degrees. So even at idle, we're at 14 degrees delta T now, rather than 7. And that actually helps. This was an astounding result. So when we actually put full workload on the servers, you could see all the CPU temperatures bunched up to 75 degrees, which is what we wanted to happen. So it maintained the temperature. So even if the default settings would allow the temperatures to go above 75 degrees, we maintain them at 75 degrees. And you can see as you switch from full load to idle, you get a bit of a drop, but you can see that the delta T was maintained and back up to 13 degrees, which is what you'd expect. So taking control of the fans doesn't necessarily mean that you save energy all the time. You save energy at partial load, because I think they're very conservatively set up. So here you can see now we're using 450 watts on the cooling. We got a much larger delta T. This is at idle and a much lower PUE, or smaller PUE. And the server fans, the average server fans, is now down to 375 RPM. So, and you can see that in some of the racks, there may be some problems with the monitoring with here, but some of the racks are showing 0 RPM. Now, when you actually put a workload on there, this got us up to 95 kilowatts. This wasn't an extreme workload. You can see that your cooling power went up by a little bit, and the server fans obviously went up a lot more because they need to maintain the CPU at 75 degrees centigrade. So it's this is the control system for the cooling system, the master control system for the cooling system. So you can see how, and although I said 75 degrees, the average CPU temperature is 70 degrees there. It's because there are 2 CPUs. It's the maximum temperature on one of the CPUs at 75. The other one is probably lower. And also, we don't actually have all of them operational, all fan controllers operational. I think we've got about 10 that are not working properly. So sometimes that messes around with your averages. So I was going to, and I don't have time really, but I can just show you a quick graph here. This was, can you see that on the screen? Yeah. Oh no, you can't, because I'm in presentation mode. Okay. Maybe I won't do the demo then, because obviously when you're in presentation mode, it takes control over the... So what I can do, and if anybody's interested, we can run this. If you've got further questions on what we've tried to do here, we can show you some more data on this by connecting to Boudin from here and showing you how we are trying to come up with some better key performance metrics, but also show how the power draw can be optimized a bit better if you take control of the server fans in the way that we've done it. Okay. So I guess because I'm running out of time now here, as this is a case study, what is the call to action to the OCP community? Now we had to create a little bit of hardware because we don't have access to the BIOS on the OCP servers. These are first generation windmill servers. So the question is should data center operators be trusted to take control of the server fans? Most of you would probably say no, they shouldn't be trusted, because things can go wrong. But, I mean, what we've tried to demonstrate here is that by actually optimizing the fan speed in the servers to the particular type of cooling that we're doing, then we save energy. Not only do we save energy, we actually, this magic number called value called the PUE looks actually even better. So the question is, you know, can there be more open access to configurations of the server fans on OCP equipment that would allow us to do this in different cooling environments? So I know when you acquire servers, you know, the server guys don't really talk to the cooling guys, really. We just deploy the servers and we hope that, and everything is probably too conservative. But you could come up with a configuration in the BIOS that allows this to operate with different types of cooling systems. So something to think about, you know. So I noticed that earlier on this morning, the Open System Firmware project within OCP could be somewhere where we could make this request or put this call to action. I don't know what your views are on that, but that would be useful. So as I'm running out of time, I'll just quickly summarize. So effectively, we've created a 140 kilowatt legacy OCP data center here using Open Compute Project style data center designs with recirculation of hot air, direct fresh air, no centralized UPS. We're piloting this data center over to look at the total cost of ownership over a period of 1 year, and we're trying to get annualized figures for this. Hopefully, you know, we can, with our wind tunnel, we can characterize these. This is how we developed the PID controller for each individual server that allows us to take control of the fans. We developed that using this wind tunnel, which was very useful, and we got support from Agetic for that. And at the end of this project, there will be an open research data pilot, which anybody who wants access to this data is openly available at the end of the project, so this will be available from March 2020 onwards, April 2020, to scrutinize it for all of what I've told you about the PUE, about how we've synchronized the cooling of the IT equipment and the coolers. So with that, I'd like to thank you for your attention, and I'm happy to take any questions. So thank you very much.